Hello everyone, good morning. Myself C Patel and today I am going to discuss the gate metallurgy problem set 14. Okay, so this is the first problem from this problem set 14. The question is, for the reaction, the rate constant at 25 degrees centigrade is doubled when the temperature is raised to 45 degrees centigrade. Okay, the activation energy of the reaction is, so we have to calculate the activation energy. So basically in this problem, we have to find the activation energy, and the given of information is that the rate constant gets doubled on increasing the temperature from 25 degrees centigrade to 45 degrees centigrade. So basically we have to use the formula of in which there is the relation between the rate constant and activation energy, and that is derived from the Arrhenius equation, and this is ln k2 by k1 will be equal to Ea by R, that is the activation energy, 1 by T1 minus 1 by T2. Okay, now this is the ratio of rate constant at 45 degrees centigrade to the rate constant at 25 degrees centigrade, and this ratio is 2 because the rate constant becomes doubled. Activation energy we have to calculate here upon universal gas constant, that is 8.314 joule per Kelvin per mole, and the temperature, that is the initial temperature, is 25 degrees centigrade, but here we have to write it in terms of Kelvin, so this will be equal to 298 Kelvin minus the final temperature is 45 degrees centigrade, so again we have to write it in Kelvin, that will be equal to 318. The value of ln2 is 0.693, that is the value of this, Ea upon 8.314, and this will be equal to 318 minus 298, so this will be equal to 20 divided by 298 into 318, and the value will be equal to this one 0.69 into 8.314 divided by into 298 into 318 divided by 20, and this value will be equal to 27300 joule. And if we find this value in terms of kilojoules, then we have to simply divide it by 1000, and this will be equal to 27.3 kilojoule. So the correct option is option C. Now coming to the next problem. Now this is the next problem, and in this case the question is, the change in entropy for a following transformation is respectively: positive indicates increase, negative indicates decrease, 0 indicates no change. Okay, now this is the first reaction, SO2Cl2, that is the gas. It is going to decompose into SO2 and Cl2 gas. So in this case we know that entropy is the degree of randomness, and if the degree of randomness increases, then the entropy increases. Okay, so here there is only one gaseous reactant and it changes to two product, and both are gases. So we can see here that the molecules, the number of gaseous molecules increases. From 1 mole it will produce 2 mole, so the randomness will increase and in this case entropy change will be positive. Now coming to the next one. This is the ethylene, that is the CH2, that is the ethene or ethylene, that is in gaseous form, and we have taken n number of this ethylene, and in presence of catalyst this ethylene gets polymerized to polythene, and this is the polythene, that is the polymer, that is made from many of the mer, that is the part of ethylene, and it is a single big part. Okay, so in this case a lot of molecules will join together and will form a very giant molecule, that is, in this case the entropy will decrease, because also a lot of this will join, so the number of the gaseous molecule will decrease, and also in polythene this is in solid state, so the randomness obviously decreases, and in this case this will be negative. So randomness decreases as gas convert into solid polymer, that is polythene, so in this case delta S is negative, and also the number of molecules also decreases. Now coming to the next one, that is the iodine solid, and at 1 atm pressure this sublimes to iodine vapors. So iodine has a very unique nature, it can sublime at room temperature, so iodine vapors. So here it changes from solid to vapor, so the randomness increases, and in this case also the entropy change will be positive. Now adiabatic reversible expansion of an ideal gas. We know that in adiabatic process dq will be equal to 0, because there is no loss or gain of heat from the system, and it is done in an isolated container, so isolated system, so the dq is 0, and we know that entropy is dq reversible upon T. So if this is 0, so the whole expression will turn to be 0. So in this case there is no change in entropy, so this will be 0. So this will be positive, negative, positive, 0. So the correct option is D in this case, that is the fourth one, that is the positive, negative, positive and 0. Now coming to the next problem. The number of degree of freedom in the homogeneous liquid region of a two-component system with a tectic point at 1 atm pressure each. So we know that according to Gibbs freeze rule, this is the expression F equal to C minus P plus 2. But in the case of metallurgy or material science, we use the condensed phase rule, because the one of the parameter, that is the pressure, is constant here. So the condensed phase rule is equal to F equal to C minus P plus 1. And here we have to use condensed phase rule because the pressure is constant. Now we have to find the value of F here. Now the component, this is the two component system. So this is the degree of freedom, this is the component, this is the number of phases. So this is two component system, so the value of C will be 2. Now the value of P is the number of phases, and this is the eutectic region, so both of them will form a single phase. So this will be 1 and this will be 1. 1 will be cancelled out, and overall the value will be 2. So in this case the correct option is 2. So this is the degree of freedom. Coming to the problem 9. delta G equal to minus NFE, that is the EMF of the cell. Then we have to calculate the value of delta S now. So which of the following expression will be the correct for the delta S? Now we know that here it is given that delta G equal to minus NFE. Okay, this is the first expression, and we also know that this is the very popular equation, that is dg equal to vdp minus s dt. Okay, now if the pressure is constant, then dg will be equal to minus s dt, because in this case vdp term will be equal to 0, because if pressure is constant dp will be equal to 0. Now if we let this equation to be the equation number 2, and if we compare these two, then we will get S will be equal to minus S will be equal to, from this equation it will be equal to dg upon dt. Okay, and if you find this further, and this will be at constant pressure, remember, because here we have taken this as the constant pressure, so this will be equal to S. Now if you find the value of delta S, so minus of delta S will be equal to this is the differentiation delta G upon delta T at constant pressure. Now the value of delta G from the expression 1 is NFE, so this is minus delta S equal to D. The value of delta G is NFE upon dt at constant pressure, and if we solve it, then delta S minus of delta S will be equal to N and F are constant here, that is the number of mole of electron exchanged, and Faraday constant, and this will be equal to dE upon dt at constant pressure. So this is delta S, and this is negative sign here, so if you take negative sign on the RSH, that is the right hand side, then it will be equal to minus NF. Okay, that is, this will be equal to minus NF dE upon dt. Here we see that this will be equal to minus NF dE upon dt at constant pressure. But here remember, this delta G is minus NFE, there is a mistake here, this is minus NFE, sorry, and this minus minus will be cancelled out, so this will be cancelled out because dg is minus NFE and we have taken NFE, and this will be expression, so the correct expression will be ds equal to plus NF dE by dt at constant pressure. This is the correct expression in this case, and the answer will be this one. So we have to remember delta G equal to minus NFE cell and delta G naught equal to minus NFE naught cell, and delta S will be equal to NF dE upon dt at constant pressure. Let's come to the next problem, and the problem is this: for the cell reaction, EMF of the cell at 25 degrees centigrade is 1.26 volt, where N is equal to 2 and delta S is this much. Find the value of EMF of the cell at 85 degrees centigrade by assuming delta S to be independent of the temperature. Okay. So basically in this problem we have to use this expression. We have to calculate the value of EMF at 85 degrees centigrade. We know the value of EMF of the cell at 25 degrees centigrade. Now, so we know that from this expression we can write it as dE equal to delta S upon NF into dt. By using this expression we can write this, and in this problem it is given that delta S is not going to change, it is independent of the temperature. N is the number of mole of electron exchanged and F is the Faraday constant. So all this expression is constant, and if we integrate it from EMF 1, that is E1 to E2, and from temperature T1 to T2, we will get the required EMF at temperature T2. We know the EMF of the cell at temperature T1, so solving this we can easily get the EMF of the cell at temperature T2. Now this will be equal to E2 minus E1 will be equal to delta S. The value of delta S is given here, and this will be equal to T2 minus T1. So E2 equal to E1, the value of E1 is 1.26 volt plus delta S, that is minus 96.5 upon N, that is 2 into Faraday constant, that is 96500. T2 minus T1, temperature is 85 degrees centigrade minus 25 degrees centigrade, and we have to write this temperature in terms of Kelvin, but whether it is in degree centigrade or in Kelvin, the difference is always the same. So basically we have to write 85 minus 25, and this difference will be equal to 60. Okay, now simply we have to find the value of this expression, and if you find, this will be equal to 1.26, and this the whole expression will be equal to 0.03, negative of 0.03, and the EMF will be equal to plus 1.23 volt at 85 degrees centigrade. So this is the new EMF of the cell at 85 degree centigrade. So the 1.23 volt, that is option B is correct in this case. Thank you very much.